All right, Professor Bryant here with another Workout Wednesday installment. This video is going to be looking at solution chemistry and calculations for aqueous solutions, but also incorporating stoichiometry and balancing of chemical reactions, prediction of products, etc. So if we go and look at solutions worksheet, which is in Module G for Chapter 4, questions 6 and 7 are good questions about stoichiometry and aqueous solution chemistry and calculations. So let's take a look at number 6. Number 6 tells us that it's asking us how many grams of AgBr can be formed when 75 mils of calcium bromide are reacted with excess silver nitrate. And they want you to write the balanced equation for the reaction because you need that information to be able to move forward. So if we take a look here, number 6, they're essentially giving us that it is a double replacement reaction. Silver nitrate is aqueous plus calcium bromide, also aqueous, creates silver bromide, which is a solid based on our solubility rules, plus calcium nitrate. Again, making sure that we have phases, making sure that we have the proper number of molecules. Again, let me clear this up. This is NO3 2, and it's aqueous, right? Because calcium is a 2+ charged ion in solution. All right. So now we need to look at balancing the equation, that it involves putting a 2 here and a 2 here. Now we have a balanced chemical equation, double replacement reaction, precipitation reaction, because we have a precipitate formed. Okay, they want to know when we take 75 milliliters of 0.650 molar calcium bromide, and we have excess, that's a key word here, excess silver nitrate. They want to know how much AgBr, right? So we are looking for grams of AgBr. So what this is telling us stoichiometrically, we remember from chapter 3 that whenever we're dealing with excess, we don't have to worry about limiting reagents. We are assuming complete reaction of all of the moles of calcium bromide here. So to do that, we need to start with moles, and to get moles, we have volume and molarity. Remember, this is very similar to the stoichiometry from chapter 3. Only thing we're involving here is a new unit, molarity and volume. So since we have the volume, we can take 75.0 milliliters. We can convert that into liters, 1 times 10 to the negative 3 liters. For every liter, we end up having 0.650 moles of calcium bromide. Now, when we have moles, we then do mole to mole ratio, and we see that for every 1 mole of calcium bromide, we have 2 moles of silver bromide. Remember, silver creates a +1 ion only, so it's a 1-to-1 ratio here. So it's 1 to 2 in the mole to mole ratio. And now for every 1 mole of silver bromide, we need to look at the molar mass, and 107.87 plus 79.9, 187.77 grams silver bromide. And we are done. Plug this in the calculator. And we should produce 18.31 grams of precipitate silver bromide. And that is assumption of a complete reaction because we have excess. Okay, let's take a look at number 7. So number 7 is a problem that asks us, what is the molarity of a potassium hydroxide solution if 42.58 milliliters of potassium hydroxide are required to neutralize 25.00 milliliters of phosphoric acid, and that's 0.1350. So this is stoichiometry. It is aqueous solution calculation, and it is also titration, but we can just use stoichiometry to be able to answer their questions. So we need to write the equation first. So we are dealing with an acid and a base. How do we know that? Well, based on the structures of the molecules. So we are dealing with phosphoric acid, H3PO4. It is aqueous. We are also dealing with KOH, a strong base, which is aqueous. And we should know that an acid and a base come together to form a salt and a water. The salt in this case is potassium phosphate and water. Now, if we look at balancing this equation, we see that a 3 on potassium hydroxide will give us a total of 6 hydrogens and a total of 7 oxygens. Putting a 3 here gives us 6 hydrogens and 7 oxygens. Okay, so now we have a balanced chemical equation. And again, water is always a liquid. Now, they've told us that it took 42.58 milliliters of KOH to neutralize 25.00 milliliters of 0.1350 molar H3PO4. So what we can do is we can approach this using the number of moles that we know. They've given us enough information to know number of moles of H3PO4. How do we do that? Dimensional analysis. 1 milliliter, 1 times 10 to the negative 3 liters. So for every 1 liter, we have 0.135 moles of H3PO4. So that is telling us exactly how many moles of acid we neutralized. We need to look at mole to mole ratio to show that for every 1 mole of H3PO4 that was neutralized, we had to use 3 moles of KOH. That comes from the balanced chemical equation. Now we have units of moles of KOH. If we cancel all our units, and they've asked us the molarity, they want to know the molarity of KOH. And to get that, all we need to do is divide by volume. So we can divide by 42.58 milliliters, and we can convert that to liters. 1 times 10 to the negative 3. Sorry, positive 3 milliliters. That should be a positive 3. Now, we see that this and this kind of cancel each other out. So, if we put in our equation 25 times 0.135 times 3 divided by 42.58, we end up seeing that the molarity of the potassium hydroxide is 0.238 molar KOH. So we have used stoichiometry to answer a question in aqueous chemistry. So this is applying all your knowledge from stoichiometry and solution chemistry to be able to achieve this answer. Again, if you have any questions or want to see some more examples of the solution calculations, feel free to leave a post or send me an email. Right.